All right, continuing on with our per pixel collision detection mini-series, we're going to build on to the last application we put together. Now, if you recall, in the last application, we had set it up so that we could have two sprites, and we were always monitoring for an intersection between the two sprites. If we had an intersection, then basically we figured out the area of intersection, and then we looked at the two textures in memory that were being used on the two sprites, and we analyzed those particular locations of pixels, or area of pixels, and we looked to see if there were any pixels that were on top of one another, that were lined up, that were opaque enough to consider to be seen, so that we knew that, yep, we do indeed have a pixel collision. Now, we've got this system in place. It ended up being quite simple, and it's working very well. But now we need to move on to animated sprites. So what happens if our single sprite, let's say this guy right here, instead of being just a static ship, let's say he's got some sort of really cool wing system. That would not be these wings, by the way, that sweep in and out, right? Well, that right there is going to make a huge difference. What if they actually fold it all the way up? So they're like a butterfly. So when folded up, maybe they look kind of something like this, right? And then you had some asteroids flying by, and one flew by really close right here, but your sprite, that's the size of your sprite. So let's say we have one frame that's got the wings out. Well, we'd want a collision if this case occurred, but on this particular frame, the wings have been swept back, so if the asteroid was moving in a vertical direction and it was just coming down like such, we would not want a collision to occur. So at this point, we need to start taking the particular frame that is being drawn on the screen into account, as opposed to just, well, the upper left-hand corner of the texture, okay? So to do that, let's draw a little dividing line right here. We're going to have to revisit an old friend of ours that we wrote a few videos back. If you guys recall, we did the sprite class. I think we called it the sprite class test. I'll just write sprite class. And the sprite class, if you recall, had a texture 2D in it, and it had a timing system and the ability to, well, draw frames, okay? So we were able to give it a frame interval and all that good stuff, a tile sheet, and it would start drawing its animated frames. Now, we need to take this class and we need to merge it into our new system. So we need to import it. And once we get the class in there, then we need to switch over to where we're dealing with, just our two textures. Now we need to start dealing with animated sprites.
Right, because if you remember, the per pixel collision app uses a texture 2D within the actor class, so it's directly looking at a texture. We need to move that over into the world of the sprite so that that texture can be animated using a tile sheet.
Precisely. So this is what we've got going on. Now, to demonstrate some animated sprite action, Logan has jumped on the internet real quick and just did some quick Googling and found a couple of animated sprites that worked well. We're not going to be redistributing these engines. We're not going to be redistributing these graphics because, again, we did find them on the internet. They did not come with any copyright information whatsoever. So we're just using this for educational purposes. That's all. So feel free to get on the internet and grab some images to play with for educational purposes, not to turn around and use in any of your real projects, or jump into some sort of paint application like Photoshop and put together a tile sheet of your own. So I just wanted to point that out. You're not going to find these textures available in your download box or on the DVD. Okay, so with that, Logan, let us go ahead and get this thing set up.
Okay, well, there's a few considerations for the project itself. As a matter of fact, before we do anything to the project, we could run it very briefly and just give a review of where the per pixel app is currently at.
Okay.
If you remember, we had the two spaceship-style textures, and as those textures intersected, we have a rectangle that represents that intersection. The rectangle is drawn in green if there is no pixel collision detected, and turns red the moment it detects two pixels or more that are colliding.
And even more convenient, in the upper left-hand window, we have a little debug drawing, if you want to call it that, so that you can analyze exactly what pixels are being compared in this intersecting rectangle area.
And all this will become very useful as we start integrating the sprite animation into this application.
Exactly.
And, of course, I also have the animated sprites you were talking about. I've added two new textures, or I'm about to add two more textures to the project. I was going to review them very quickly before I actually add them.
Okay.
We can load up the first, which is a series of 6 images of an animated cat, a very pixelated cat, but that actually works out very well for us because we get a clear idea of what areas are shaded and which areas are not.
And you've got some very nice areas that kind of jumble up with pixels and then kind of clear out.
Right, we have these areas right below or right at the feet where they say sometimes there's space filled in by pixels and sometimes that space is completely cleared out. So we have a really good differential between cleared areas and filled areas.
And that's going to work nicely for us in doing some tests.
And the other image is a set of 3 mushrooms that are animated so that they stack on top of each other and then unstack. The reason I like this image is because they go from being horizontal and having a lot of free space above them to being stacked vertically and taking up a lot of space.
Okay.
So those are the 2 images. And while we're looking at them, we might as well get them copied into the project. So I'll bring up my projects folder for Visual Studio. Here's our per pixel collision project. So we can jump into its content project and drop them in. Then, of course, we have to go back to Visual Studio and add them as existing items, import them. So here we are under the textures folder. There's our new cat and our new mushrooms pictures. So that takes care of the graphics we'll be working with. Now, the next thing we need to do to really get this step of the project kicked off is we need to import our sprite class. We have the sprite class written in a separate project, so I'm going to copy it over to the per pixel collision project and add it as well into the classes folder. So that means we need to go back here. We're currently under the per pixel collision project, so I'm going to jump up a few levels until we can see our sprite class test project, the project in which we wrote the sprite class. Jump in a few levels, we'll grab the classes folder, and there is our sprite class. So I can copy that file, jump back up, go back to the per pixel collision project, into its textures folder, or excuse me, not its textures folder.
I said engines and you went into the textures folder, so we're even.
So yeah, wires crossing, but yeah. Well,
so into the classes folder. Very nice.
Classes folder. Paste that right next to actor, so that inside of Visual Studio we can go to the classes folder, add an existing item, and bring in our sprite class.
Okay.
And after bringing it in, I'll load it up as well.
And make some changes like to namespace.
That's a good point. The namespace is set based on that project, meaning it says sprite class test. I would rather have that class available in the per pixel collision namespace.
Kind of makes sense.
Inside of sprite, we'll change that.
Okay.
All right, now let's take a look at some of the actual considerations to integrate this into Actor. And the first thing would be inside of the Actor class itself, we'll go and change the texture property to be a sprite property. So the type, of course, is going to be of type sprite, and we can call the field sprite as well, just to mimic what it was using for texture.
Okay.
Now, a few other things have to be set up, and that is any case where the sprite differs in its properties to a texture. Some of the things should come along. If you remember, back in the sprite class, we had given sprite a width and a height property, properly using tile width and tile height instead of the overall texture width.
Exactly.
So we've got that set up. But there's going to be several other concerns for the way this is working. I could, to make a lot of those more apparent, I could run a build, and we should get quite a few errors, as there are many things that don't work for texture now. As a matter of fact, a lot of the code changes here were referring to the actual field name texture, and those need to be changed to sprite now. So the first case of this is going to be within the bounds property, which is trying to use the texture's width and height. This, of course, needs to be changed to the sprite field. And let's see. After sprite, we have the draw method, where draw was making a call to the given sprite batch and feeding in the texture. This will have to be changed around a little bit because we're not going to draw the sprite's texture. Instead, we're going to tell the sprite itself. So this dot sprite, it has a draw method. So we're going to tell that draw method to run. Now we've got a sprite batch that we need to feed it, and we'll feed that over. Sprite needs to be given a position in order to draw it. Well, being that this is an actor class, we have a position to feed it. We can give it this dot position. All right, we can build, and that should take care of a few of the errors. Let's see what's left to update here. So we've changed the draw call, and down here in the collision section, there are some texture references inside of the check collision method itself because the actor was looking at its texture to get data. There is no texture stored in an actor. Instead, it's stored in the actor's sprite. So if we wanted to get actor A's pixels, we'd have to first look at its sprite. Now, of course, texture is a public property of a sprite, so we can simply read the texture data from the sprite itself. So we can build there. And let's see. Now, one other thing to consider, and that is for the sprite animation to work, the sprites update method has to be called. So here we have an update, and that's where we get the relevant timing information in order for the sprite to update properly. Now, up until this point, Actor didn't have an update function because it wasn't animated. It wasn't really active. All it did was draw. So we're going to add in an update method for the sprite, or for the actor itself. So let's see. Let's take a look at sprite. I think it was just a public void. I'm making sure that the signature matches what I had back over the sprite, so I feed the proper information over to it. So this is going to be a public void method called update, where we will take in a game time parameter. And inside of this new update method, all we're going to do is call our sprite's update method to make sure that the proper timing information gets passed along to the sprite, and make sure that the animation itself takes place. So as simple as that. Alright, moving on. You can see that there's still quite a few errors left, and all of these errors now appear within the game class. And inside of game, if we go down to load content, you can see that that's because we're trying to address the texture field of an actor. And we need to change this over to a sprite. As a matter of fact, this is the area where we need to create the actor's sprite. Because if you remember, sprite has its own constructor where it sets up many different properties of the sprite itself.
That's right.
So let's replace this with actor1.sprite. And we'll set that equal to a new instance of sprite. Now the first thing that the sprite is going to need to take in via the constructor is a texture 2D. So I'll leave this call to content.load in place, and then add in a comma, and we can specify the rest of the parameters for the sprite. The next thing to add is the tiles in X. Now before I use the new textures, I'm actually going to create sprites based off of the existing textures. And that means for these single frame non-animated textures, they're going to have a tiles X and Y of 1, because there are no further tiles within it. And the frame rate is really irrelevant here, so I'm just going to set it to 1 second, or 1 frame per second. And we'll worry about changing them to the actual new textures after we get everything working under the new sprite class. So at this point we can do the same treatment to actor 2. We can set it sprite, and then we'll create a new instance of sprite. We'll leave the content texture loading in place, add in a tiles X and Y of 1, and a frame rate of 1 as well, since, again, with no animation we wouldn't be able to see that effect anyway. So now if we build, we're really starting to cut down on errors. We have only 4 left. So before we get too much farther, I do want to remember inside of the update method to update the actors, because if the actor is updated, we'll in turn update the sprites. So before we move past update, I want to make a call to actor1.update. And of course we need to feed it our game time, and do the same to actor 2. And of course we're updating these actors individually because we have not put in any kind of actor management system. So that has our actors updated. And let's see, down here in draw, one of the final areas of some problems is down here in this debug draw method, where we're once again trying to directly access a texture which no longer exists as a field inside of the actor. Instead, that is part of the sprite. So we'll add in sprite.texture for each of these. And I do want to keep this debug method, because this is going to show us what's up with the pixels gathered from the animated sprite versus the non-offset animated sprite. And there's 2 more errors. Let me jump to those to find... Oh, okay. I had skipped over some in positioning the actor, where we're using the texture's width and height. That is no longer the texture. Instead, in this case, we can look directly at the sprite, because the sprite has a width and a height property. Now we can build. Everything is taken away. And let's see if we can run the game now running under the new sprite system. So everything looks like it's working. As a matter of fact, we have what looks to be identical functionality to before. So why go through all of that effort to get the same result? Well, since we're using sprites, we now have the ability to use animated tile sheets. So I could change this ship texture to the cat texture. Now, if you remember, the cat had 6 tiles across and only 1 tile down. So we can change this to 6 by 1. And there's not many frames, so I'll give it a slow frame rate of 5. For our actor 2, we could change that to the mushrooms picture. And that had quite a few frames, so I'm going to give it a frame rate of 15. So now if we run...
Do you want to give it something other than 1 and 1?
I do, because this is the undesirable result that has happened. So, yes, I most certainly do. As a matter of fact, I believe that is 5 tiles by 4 tiles for the mushroom texture.
Much better.
So there we go. We don't see the entire tile sheet. We see just the relevant frame. But there we go. Now we've got our per pixel collision application running with animated sprites. Mm-hmm. But there's still a few adjustments that need to be made. If we look at the collision, we can see that we do, in fact, get areas with rectangles with no collision, and then with per pixel collision, but they're not exactly correct. Here in this case, it looks like that one mushroom should be going through the cat's feet. But, I mean, we can see the pixels colliding, but nothing actually happens.
We get an honest answer up in our little debug area at 0, 0.
And that's exactly why I left that. You can see that the texture in the debug area up at the top left corner of the screen is not animating.
That's right. And that's a look at the pixels we're comparing. So we're not comparing animated pixels here.
Right, and if we watch those pixels, the collision coloring result makes sense suddenly, because you can see that the cat's paw is not animated there. So here we have no collision. Move up 1 pixel, and then we do have a collision.
That's right.
Now, of course, to get the correct result, we need to make these collisions respect the current frame of animation. So where would be a good place to do that? Well, the idea here is that inside of Actor, we already have to normalize the given collision rectangle to a relevant portion of the source texture.
Right.
Now, the source texture has become the texture held in the sprite sheet. And the sprite sheet is broken up, and we know how to break it up because of the sprite's frame bounds. As a matter of fact, the very reason to have sprite is really this core property right here, the frame bounds property, which is able to look up rectangular coordinates based on the current frame. So we could use those coordinates, and those coordinates represent one of the tiles out of that overall sheet, the current animated tile. Mm-hmm. So if we use this frame bounds, X and Y, we should be able to offset our normalized bounds and tell the collision system to look at the current frame of animation. Now, before I do that, of course, I need to change this property to be public so that we can access it outside of Sprite. And I'll change the casing on that as well. I'll hit F2 to refactor the name frame bounds so that I can replace it with a capital F. And we'll apply the refactoring. Now we can go over to Actor. Inside of normalized bounds, of course, we're normalizing to the current actor's position. But this, as we saw, puts us at the first frame, the top left frame of that sprite sheet.
That's right.
Now we'd like to offset by whatever the current frame's location is. So that would be this dot sprite dot frame bounds dot x. Since on the first line of that we're looking at the x component. And then we could do the same thing for y. We could also offset in the y by this.sprite.frameBounds.y.
Exactly, and this is how we simulate looking at the correct frame.
Exactly.
But again, it's still just one tile sheet. So we're looking at, a particular area of pixels on this tile sheet. But again, we're breaking it down to where it's like we're looking at a particular frame.
Exactly, because those different tiles have their pixels possibly located in a different position in order to give the illusion of animation.
That's right.
And we need to be looking at the appropriate frame so that the pixels are in the right location for the visual result.
Exactly.
So now if we run, we can watch in the top upper left-hand corner and see that now our debug textures are also animated in accordance with the current frame. And also, if we watch the visual result, we get what looks like a correct result.
And if Logan takes his hand off the mouse, look at that. So Logan's not even touching the mouse now, and we've got some green frames, and we've got some red frames.
So more of in the space fighter scenario you had laid out, if we had a ship with adjustable wings, we would now have a scenario where, without input, the position of the wings could drive whether or not there's a collision with nearby objects.
Exactly.
And with that, I think that's all I needed to cover in this video. Again, the goal was to get our sprite animation system integrated into the per pixel collision app so that we could use animated sprites with per pixel collision detection abilities.
Exactly, and it really wasn't all that difficult. It was more or less just bringing in the sprite class and then making Actor have a sprite and then going through and making the appropriate adjustments so that the two played nicely together. And then really, at the end, the big thing was just inside the normalized bounds, just updating it so that we were offsetting properly to simulate looking at a particular frame. Basically just shift around on that tile sheet so that we're looking at the right set of pixels.
Exactly, so that way we collide with the current frame as opposed to frame 0.
Exactly. And with that, that is going to wrap up this video. And does that pretty much conclude everything we were going to do in the 101 class for per pixel collision?
There is one last thing, and that is we have the system of actors now animated, now with per pixel collision, The only thing I don't like about this system for the use in Spacefighter is the fact that up to now, this actor class has its origin at the top leftmost pixel.
Okay.
And that gives more of a rectangle style of movement and positioning. And in a game like Spacefighter, it is more convenient to have the actor's origin located at its center, not at the top upper left-hand corner.
Right.
So there should be one more video that will follow this one, where we'll cover the adjustments necessary to draw these sprites around a centered origin and make sure that all of our collisions still calculate properly.
Okay, fantastic. So we'll be right back with that video. Thanks a lot, guys.